Imagine you are playing a board game where you can walk on squares that have letters on them. In a deterministic machine DFA, you always know exactly which square you must step to next based on the current square and the rolled dice. An NFA non-deterministic finite automaton is like having many possible paths you can follow at the same time. You can split into several copies of yourself, each trying a different route. This many-at-once idea is useful because some languages' sets of strings are much easier to describe if we let the machine guess which way to go. For example, the language of all strings that contain the word cat somewhere inside can be described with a tiny NFA that simply guesses the position where C starts, while a DFA would need many more states to remember how many characters have been read. So NFAs give us a simpler, more intuitive way to recognize patterns, especially when the pattern has choice or optional parts. Formally, an NFA is a 5-tuple M equals Q sigma delta Q0 F. Q is a finite set of states, think of rooms in a house. Sigma is the alphabet, the set of symbols the machine can read, like the letters A to Z. Delta maps a state and a symbol or epsilon to a set of states. It tells us all possible next states. Q0, an element of Q, is the start state. F, a subset of Q, are the accepting final states. Example, let sigma equal the set, and B we want to accept any string that ends with a B define. Q equals the set Q0, Q1, Q2. Q0 is the start state, F equals the set Q2. Delta of Q0 and A equals Q0 and Q1. On an A we can stay in Q0 or move to Q1. Delta of Q0 and B equals Q0, any B keeps us in Q0. Delta of Q1 and B equals Q2. If we guess that this A could be the start of a B, a following B takes us to the accepting state. All other state and symbol pairs give the empty set. No epsilon moves are needed here, but we could add one. For example, delta of Q0 and epsilon equals Q1, meaning we can jump to Q1 without reading a symbol. This tiny NFA recognizes exactly the strings whose last two letters are a B. When an NFA reads a word, it may be in many states at once. Two tools help us track this. Epsilon closure of state : the set of states reachable from state by taking 0 or more epsilon moves. Formally, epsilon closure of S equals the set of Q such that Q can be reached from some P in S using only epsilon transitions. Move of S and a : the set of states we can reach from any state in S by reading symbol A, follow a regular transition, and then taking the epsilon closure of the result. Mathematical example: use the NFA from the previous item, but add an epsilon move from Q0 to Q1. 1. Start set : S0 equals epsilon closure of the set containing Q0, which equals the set containing Q0 and Q1, because we can jump to Q1 without reading. 2. Read the first symbol : move of the set containing Q0 and Q1 with a equals epsilon closure of delta of Q0, a union delta of Q1A. Delta of Q0 A equals the set containing Q0 and Q1. Delta of Q1 A equals the empty set. Union equals the set containing Q0 and Q1. Its epsilon closure is still the set containing Q0 and Q1. 3. Read the next symbol B : move of the set containing Q0 and Q1 with B equals epsilon closure of delta of Q0 B union delta of Q1B. Delta of Q0B equals the set containing Q0. Delta of Q1B equals the set containing Q2. Union equals the set containing Q0 and Q2. Epsilon closure adds nothing new, so we end in the set containing Q0 and Q2. Since the final set contains an accepting state Q2, the word a B is accepted. The NFA accepts a word if and only if after processing all symbols the current set of states intersects the accepting set F. Explanation: even though NFAs seem more powerful because they can guess, they actually recognize exactly the same languages as DFAs. The standard way to turn an NFA into a DFA is the subset construction, also called powerset construction. Each DFA state corresponds to a subset of NFA states. Step-by-step example: same NFA as before without epsilon moves. 1. Compute epsilon closure of the start state. S0 equals set containing Q0. This becomes DFA state A. 2. For each alphabet symbol, compute move. Move a comma a equals set q0, q1, arrow new df a state b. Move a comma b equals set q0, arrow stays at a. 3. Process state b. Move b comma equals set q0, q1, arrow stays at b. Move b comma b equals set q0, q2, arrow new df a state c. 4. Process state c contains accepting q2, so c is accepting. Move c comma equals set q0, q1, arrow b. Move c comma b equals set q0, arrow a. No new subsets appear, so the DFA is. States a start b, c accepting. Transitions, a dash a arrow b, a dash b arrow a, b dash a arrow b, b dash b arrow c, c dash a arrow b, c dash b arrow a. The DFA has exactly the same language as the original NFA, but now it is deterministic. From any state and symbol, there is only one next state. The construction may create up to 2 to the power of size of QDFA states, which explains why DFAs can be exponentially larger than NFAs. One of the biggest reasons we like NFAs is that we can combine them easily to build automata for larger languages. Union L1 Union L2, take 2 NF as M1 and M2. Build a new start state Q0 with epsilon moves to the start states of M1 and M2. The accepting states are the union of the old accepting sets. The new machine accepts a word if either M1 or M2 would accept it. Concatenation, L1 concatenated with L2. Connect every accepting state of M1 to the start state of M2 with an epsilon move, then make the accepting states of M2 the only accepting states of the new machine, and optionally turn the old accepting states of M1 into non-accepting. This forces the machine to first finish M1, then continue with M2. Clean star L1 star. Add a new start accepting state Q0. Add an epsilon move from Q0 to the old start of M1, and epsilon moves from each old accepting state back to that old start. This lets the machine loop any number of times, including 0 through M1. Illustrative example. Suppose L1 equals a NFA with a single transition Q0 a arrow Q1, and L2 equals B similar. Union gives an NFA that accepts O or B, one epsilon move to each sub-machine. Concatenation yields an NFA that accepts a B epsilon move from Q1 of the first to start of second. Star on L1 gives an NFA that accepts any number of A's, including the empty string epsilon move loops back to start after each A. These constructions are extremely systematic, which is why regular languages are closed under union, concatenation, and star. Sometimes we need to go backwards. Given an NFA or DFA, we want a regular expression that describes exactly the same language. A common method is state elimination. The idea is to repeatedly remove a state, redirecting all paths that entered and left that state with a regular expression label that records what was read. Example procedure: NFA for language of strings ending with ob. Step 1. Add a new start state S with an epsilon move to the original start Q0, and a new final state F with epsilon moves from each original accepting state Q2 to F. Now we have S, Q0, Q1, Q2, F. Step 2. Eliminate Q1. Find all incoming edges to Q1 from Q0 on A, and all outgoing edges from Q1 to Q2 on B. Replace the two-step path Q0 A to Q1 B to Q2 by a single edge Q0 A B to Q2. Remove Q1 and its edges. Step 3. Eliminate Q0 if needed similarly, creating a direct edge from S to Q2 with an optional AB, and so on. Step 4. Finally eliminate Q2, creating a single edge from S to F, where R is the regular expression that results from concatenating all labels found during elimination. The resulting regular expression for this tiny NFA is O or B star a B, which indeed describes all strings ending with ob. State elimination works for any finite automaton, though the intermediate expressions can grow quickly. Careful ordering of eliminations keeps the final expression manageable. Explanation: the choice between using an NFA or converting it to a DFA depends on time, how fast we can process each input symbol, and space, how many memory cells we need. NFA simulation. At each input character, we keep a set of current states. Computing the next set requires looking at all outgoing transitions of every state in the current set. If the NFA has n states, the worst-case time per symbol is O of n, and the space needed is O of n to store the set. DFA simulation. A DFA has exactly one current state, so each step is O of one time. However, the DFA may need up to 2 to the n states after subset construction, which can be huge. Space needed is proportional to the number of DFA states, often stored in a transition table. Quantitative example. Consider an NFA that recognizes the language of all binary strings where the kth last bit is 1. This NFA needs only k plus 1 states, it remembers how many bits it has seen. The equivalent DFA would need 2 to the k plus 1 states because it has to remember the exact last k bits, for k equals 10. NFA, 11 states, O of 11 approximately O of 1 memory, each step examines at most a few transitions, very small runtime. DFA, up to 2 to the 11 equals 2048 states. Transition table of size 2048 times 2 approximately 4096 entries. Larger memory and possibly cache miss overhead. Thus, NFs are often preferred when the underlying regular expression is complex. Many alternations, optional parts because they stay compact, while DFs are ideal when we need guaranteed constant time processing and can afford the space. For example, hardware pattern matchers. NFAs are not just theory, they power many real tools we use daily. Pattern matching. Regular expression engines like those in Unix grep, Python Ray, or JavaScript first compile a pattern into an NFA, often called a Thompson NFA. The engine then simulates the NFA on the input text, which allows features like star, question mark, and pipe to be handled naturally. Lexical analysis. A compiler's lexer turns source code into tokens such as identifiers, numbers, and operators. Tools like lex or flex generate NFAs from token specifications, combine them using the union construction, and optionally convert to a DFA for fast scanning. The resulting scanner runs in linear time over the source code. Network intrusion detection. Systems such as Snort use NFAs to match packet payloads against thousands of regular expression signatures simultaneously. Because NFAs can share states, they can test many signatures in parallel without building a gigantic DFA. Real-world scenario. Imagine you type a search query in a code editor that highlights all occurrences of the pattern for \s plus \w plus \s plus in plus \w. The editor builds an NFA for this pattern, runs the NFA over each line of code, and instantly colors the matches. If the engine tried to convert the NFA to a DFA, the number of states could explode due to the \s plus any amount of whitespace and \w plus any identifier, making the editor slower and using more memory. Hence, the NFA-based approach gives a responsive user experience while keeping memory modest.